Okay, so today we're not going to look into the Portland Cement Association method. The initials are standing for Portland Cement Association. And this method is for rigid pavements. It's based on mechanistic studies done by Westergaard, very famous author. And it has several design considerations. The method will tell you the thickness of the concrete layer and the thickness of the subbase, if there's any, will also be part of the design approach. So as design factors, we have the flexural strength of the concrete. That will be read as modulus of rupture in megapascals. This method is in international system units. We have the subgrade strength. When you have a subbase, then you combine the subgrade and the subbase together, and you produce a combined bearing capacity for the concrete from this subgrade and subbase. In this case, it's much simpler than AASHTO because we only use a couple tables. I will show you soon. We also have the weights, the frequencies, and the type of axle loads from the trucks. So this is different from the ESAL. In the ESAL, you take all the axles from different trucks and you use the load equivalency factor to express them as a standard axle. In this case, you don't do that. Instead, you keep the axle separated and you estimate the amount of the life that every axle consumes from the pavement. And you consider the number of each axle for a given weight groups. And this is done through the life or design period of the pavement. Okay? No, it was here, design period. Okay. Now, this is using the fatigue cracking as one of the two design considerations. And the fatigue cracking happens near the edge, midway between joints. So if you see here, where my pointer is, this will be the joint. Your dowels will be here. And this will be your shoulder. So the fatigue cracking will happen here, halfway between this joint and the next one, and towards the shoulder location. So this is one out of two. The second criteria is erosion. Erosion, we investigated and explained erosion last time for AASHTO. And erosion is happening in the joint and the corner. Okay? So these two design criteria are part of the method. We need the flexural strength of the concrete as the characteristic of the strength of this concrete. And we will do that at 28 days, as is usual. And this will control the cracking of the pavement. Now, for the subgrade and subbase, we will combine the two of them using these tables over here. So what we obtain is a combined value for both of them. So for instance, imagine you have, let me just try to bring that. Yeah, so imagine you have 100 millimeters subbase. Untreated means it's granular. If you have 100 millimeters, which is 10 centimeters, is small, and your subgrade soil K value is 20. The effect of the subbase, when you consider all together subbase and subgrade soil, is an equivalent capacity of 23. If you have 20 and you provide now 300 millimeters of subbase, the equivalent combined effect of the subgrade and subbase is 38 megapascals per meter. Now, this is for untreated or granular. It's the same. That's what it means. The cement treated subbase provide a way higher increase in the combination. So for instance, the same 20 megapascals per meter with a 100 millimeters of cement treated subbase will triple the value of the foundation to 60. Why? Because the subbase is treated with cement, so it's like a cement, it's like a concrete layer. Poor quality as compared to the top layer, but way much better quality as compared to the subgrade soil. The Portland Cement Association provides some equivalencies between different methods and the modulus of subgrade reaction, which is the one they use in megapascals per meter. So if you have ASTM soil classification, if you have AASHTO soil classification, Federal Aviation, or any other thing like California bearing ratio, you can get equivalency values from there. We also have to consider what is our design period. The design period for highways is advised as no more than 20 years. For urban roads, it can be extended to 30, 35 years. In this method, we will have the projection factor depending on the yearly or annual growth rate. So this is not an accumulation factor. This is only to project what is the equivalent traffic if we grow constantly at a given rate. So for instance, if you grow constantly at a 3% rate every year, today's traffic being 100,000 vehicles will be 1.3 times that. So it will be 130,000 vehicles, but that is not accumulated. That is just the projection in 20 years. Why? Because the method is considering traffic is slightly different than the AASHTO method or the ISALS method. We will see how. We will have the weight and the axles. So, for instance, if you have single axles, these are the weight groups. The heaviest is 125 to 133. It goes down all the way to 44 kilonewtons to 53.3 kilonewtons. That is the weight on the axle. The type of axle is single. If you go to tandem axles, the highest weight will be the group of 213 kilonewtons to 231 kilonewtons. And the lowest will be the one between 53.3 and 71.1 kilonewtons. This is the weight you have in that axle. The axle is a tandem axle. Now, when you have a given axle, let's say the 125 to 133, we will be considering the axle repetitions per 1,000 trucks. This is based on US average values. If you have site-specific traffic counts, then you can replace that. And instead of using this per thousands, you will use whatever you are reading from the site. This will be the case when the pavement is existent. The pavement is arriving to the end of the service life. You have to plan for the reconstruction of that pavement, and you have statistical information that tells you what is the percentage. So for instance, this could be a 1%. For instance, this could be a 20%. I don't know, it depends, but you will have those values. So for today's class, I'm gonna use the one that is based on the method itself. So I will estimate the total number of trucks and then use this per thousands to know how many truck repetitions we have for different axle groups. We have a load safety factor that will increase the weight that you observe. So in this first group, for instance, your weight maximum is 133 kilonewtons. But if you are on a multi-lane highway with high volume of trucks, then you will apply a load safety factor of 1.2. That means the 133 I have here is gonna get multiplied by 1.2 and it's gonna go to 160. That is the maximum weight on this axle group. Why? Because that weight is gonna serve to estimate how much this is producing damage on the pavement. The load safety factor will be 1.1 when you have an arterial or highway street with a moderate volume of truck traffic. And the load safety factor will be 1 when you are looking into residential streets or small volume truck traffic. The design method used this template. The template has the trial thickness. I'm gonna put it in presentation mode. So the template has the trial thickness. You have to test the thickness you think you want to use. So let's say 200 millimeters. You need to put here the sub-base, subgrade, K value, the combination from the table I showed you before. You have to put here the modulus of rupture of the concrete. You have to put here the load safety factor, the one I just showed you now. Then you need to decide if you want to use dowels, yes or no. But probably, as you learned from last time, you will use the dowels most of the time, especially when you are using a pavement that doesn't have any reinforcement. And whether you want to have concrete shoulder, yes or no, and what is your design period. So that is the header of the form. Then in the tables, you will have the type of axle, single axle. Below this one, you will have the tandem axle. Below that one, you will have the tridem axle, okay? For the single axle, you will have the axle load of the group, the maximum. So as we saw before, that will be 133, 125, 115. So that 133 will come here, 125, 115, etc., etc., etc. Then you multiply that by the load safety factor. So the 133 by 1.2 will give you 159.6. The 115 by 1.2 will give you, and so on and so forth. The next column is the expected repetitions. The expected repetitions are based on the table 5. I'll show you that table in a moment. The next 2 columns are for the fatigue analysis, and the following 2 columns are for the erosion analysis. They will have the allowable number of repetitions, which you will be reading from a specific figure, a chart with a graph. And the percentage of fatigue will be the expected repetitions divided by the allowable repetitions. So if the expected repetitions are 1,000 and the allowable repetitions are 10,000, the fatigue percentage will be 10%. That single group will have consumed 10% of the capacity of the pavement. You go to the second one. If the expected repetitions are 1,500 and the allowable are 3,000, you will have consumed 50% of the life of the pavement here. And you carry on the analysis all the way up to the last group for single and for tandem and for tridem. And then you add them all. And that summation has to be less than 1 or 100%. For the erosion, you will be reading the allowable repetitions from a table, from a figure, pardon, and you will be doing expected over allowable, that will be your damage. It's the same concept. The column 1, you enter these axle load classes as explained before, and these load classes will drop by 8.9 kilonewtons. And they start with the highest, which is 133 kilonewtons. It is always the case you take the upper bound for each group. And the single axles are entered on the top half of the chart, and the tandem are in the bottom half. The tandem axle increments will be 17.8 kilonewtons. And the typical largest tandem is 231 kilonewtons. Now, for the design traffic, these are the steps. You will have to estimate what is your low safety factor, and you will keep it somewhere over there. The traffic analysis should tell you the forecast on the average daily traffic that you expect to have on the road, the ADT. This is in one day in 2 directions. You multiply that by the truck percentage. So that gives you the total number of trucks in the 2 directions, all lanes, and in 1 day. You multiply that by 0.5. That gives you the total number of trucks in 1 direction in 1 day. You multiply that by the lane distribution factor, which we have a figure, I show you soon. And that gives you the total number of trucks in the design lane in 1 day. You multiply that by 365, that gives you the total number of trucks on the design lane. This thing keeps on advising something. You multiply by 365, and this is the total number of trucks in 1 year on the design lane. You multiply that by n, the number of years for the design period, and this is the total number of trucks on the design period. But the design period is not considering the growth of the traffic. So you have to include that growth of that traffic in here by adding the growth factor. Once you have done that, you have total number of trucks on the design lane, on the design life, or design period. That is what we call the design trucks. You divide them by 1,000 so that you have design trucks on the design lane on the life of the road per 1,000. The per 1,000 is on purpose because this statistic is per 1,000, as you see on column 3. So when you do 0.58, you multiply by the total trucks on the design lane, on the design life per 1,000. Otherwise, if you multiply by the total number of trucks on the design lane, on the design life, you will have to divide by 1,000. So to avoid that division, you work out that division right here. And this RJ is the number, the per 1,000 value that you read from this table. So the 0.58 is the RJ for this group. The 135 is the RJ for this group. The 277 is for this group, and so on and so forth. The equivalent stress is estimated from tables 6A and 6B, and is a function of the subgrade strength and the slab thickness. The values are given for single and tandem. So I'm going to show you 6A. So for instance, let us imagine we are designing 200. And let us imagine our K of the subgrade subbase is 20. In that case, my equivalent stress for the single axle is 204. And my equivalent stress for the tandem axle is 1.9. Let us imagine you add the cement stabilize, as we discussed before, and you go up to 60. In that case, your equivalent stress for single is 167, and your equivalent stress for tandem is 142. Now, let us imagine for some reason you landed somewhere in between 40 and 60. Let's say it's 50. In that case, it is the equivalent stress for the single axle is somewhere between 1.67 and 1.8. So you can simply make the average if you want. And for the tandem, it will be somewhere between 142 and 158. So you can get the average if it is a SAC 50. If it is 45, then you have to break this in chunks, like you did contours in surveying, and then estimate what it is. The stress ratio is the equivalent stress you calculated before divided by the modulus of rupture of the concrete. And this is what you use to estimate the allowable load repetition. So when we go back in the template, that is how you estimate 8 equivalent stress. The equivalent stress is coming from table 6A or 6B. And the stress ratio is that equivalent stress divided by the modulus of rupture. Now, why do we have table 6A and 6B? We have two tables because table 6A is for no concrete shoulder, and table 6B is when you do have a concrete shoulder. As a matter of fact, I need to continue with the next slide, so just a second, please. Now, for the erosion analysis is similar. You will read erosion factors from table 7A, 7B, 8A, or 8B, depending on the type of joint and type of shoulder. So I'm going to show you one of them. 7A is this one. And this is erosion factor. Dowels is a yes. Concrete shoulder is a no. So imagine, for instance, let me just bring the arrow I was using before. And this arrow is not very clear, so. So imagine you decide that you do want dowels, yes, and you don't want concrete shoulder. And you are gonna test the 200 millimeters. And your subgrade subbase combined modulus is 80. In that case, your erosion factor for single will be 281, and your erosion factor for tandem will be 291. When you have a midpoint value like 70, your single erosion factor is somewhere between 281 and 282, so it's 281.5. And for tandem is somewhere between 291 and 294. So it is probably 292, 293. 292.5 probably. But it depends how far you are, right? So you interpolate. So you estimate your erosion factors. And then in column 7, you enter the erosion damage that you are gonna be reading from figure 6A and 6B. Figure 6A and 6B is this figure. Basically what happens is we define a pivot point. So let's imagine my erosion factor is 3, exactly 3. My pivot will be here, it will be fixed. It's not gonna move anywhere. And I will be reading the weights. If you remember, the single axle is 133, and if the load safety factor is 1.2, then this will go to 160. So my 160 will cross through the pivot, and the allowable will be the value that I hit here. In this case, 100,000. So that is the overall approach that we are going to follow. Okay, so maybe it's time for us to do an example. So let us have this divided highway. The divided highway is 4 lanes. We have a design period of 20 years. This ADT for this road, it looks like this is not gonna give up, huh? The ADT is 15,000 vehicles. The truck traffic is 19%. And the growth rate is expected to be 4%. And we're expecting 360 days per year. So, this is a multi-lane. And we have a significant number of trucks. That means that most likely we will use a high load safety factor. How much? Multi-lane, high volume of trucks, low safety factor 1.2. Not to be confused with lane distribution factor, is this one, right? Now, let's go back to the example. Oh, sorry, I failed to mention. We are designing a plain concrete pavement with dowel joints. So it's plain concrete with dowel joints. So let us go back here and say dowel joints, yes. We have no concrete shoulders. We will have 100 millimeter untreated base. And the subgrade soil is clayey subgrade with CBR of 8. So my CBR is 8. And I am reading modulus of subgrade reaction somewhere between 40 and 60. We have 1, 2, 1, 2. It's almost an even split. Because if you see the scale shrinks as I move to the right? I have a big space between 20 and 40, and I have a very short space in the last one. So as I move 40 to 60, the space shrinks, 60 to 80 shrinks, 80 to 100 shrinks. This is 100 to 140, so it's a big increase. So maybe 50, we might say. That means I am going here with a 50, and it's untreated. So I'm going with a 50. It's halfway between these two. And it's untreated and 100. So it is 100 untreated. We said this is close to 50. In that case, it's halfway here. In that case, it's halfway here. So this is 45 to 64 halfway. So we have almost 20, 19 to be exact. So that means we have 55, 54, 55 approximately, the K value. We have also F prime C, 32 megapascals at 28 days. F prime C is 32 megapascals. We put the 32 here and we multiply by a K value. The K value is 0.7 if you have crush aggregates. And it is 0.8 if you have round aggregates. So let's imagine we have crush aggregates. 0.7. So square root of 32 first. By 0.7. So we have 3.9597. So 3.96 is modulus of rupture. Track percentage, we say is 19%. Directional split is 50. Now, remember, we have 15,000 vehicles two ways. We will go into this table here. And we're going to have in one direction 7,500 because the two directions are 15,000. So we entered this with 7,500. This is 8,000 here. This is 6,000 here. 7,000, 7,500. And we hit the two lanes in one direction. And we read here. So this is 0.9, this is 0.8, this is 0.85. This is probably 0.83. Traffic growth is given 4%. ADT 15,000. Design period 20 years. And now we need to test a thickness. So what thickness do you guys want to test? Give me a value, please.
Anything, doesn't matter.
150.
150, I hear. The trucks in the design period will be 12. Okay, let me put commas to this. The spreadsheet will calculate it for you. Okay, I need to check this number.
So the original file I have, it says 0.5, not 50. So that could be a reason if the final result doesn't make sense.
This should be like 12 million, not this
So
many.
if you change 50 to 0.5, put the cell underneath 50, put in 0.5 instead of 50.
Oh, yes, yes. Thank you.
No problem.
Yeah, thank you. Sorry. If I tell you what time I woke up today, you won't believe it.
You reply to my emails at like 5, 6 a.m. I don't know how you do it.
Yes, I woke up at 3:20
Um,
in the morning. So that's the reason why my brain is almost toasted at this time. Thanks. So yeah, it's 12 million, almost 13 million. Now, we also need the projection factor, which will come from this table. So we're looking at a 4% growth on a 20 years. Projection factor is 1.5. So I don't know how much is going to be the equivalent stress. I don't know how much is going to be this. We're going to go figure it out. Okay. But we already know that we have 150 trial thickness and 54 megapascals. And we have dowels, yes, concrete shoulder, no. So we have here concrete shoulder, no. Doesn't say anything about the dowels in this one. And the other table we have is concrete shoulder, yes. But the one we have to use is this, no concrete shoulder. And we are starting with 150. The K is 54.5. So we go back there. That means that the equivalent stress for single axle is somewhere between 40 and 60. Is halfway will be 50. And then halfway again will be 55, which is, that's where we are. So we have from 270 to 251. This is the difference for the whole span. And we divide this difference over 4. And we take that away from, and we add that to 251. So it's 2.51 plus that. So I'm interpolating, okay? I'm just doing interpolation. It's 255.75. The stress ratio is simply the 255.75 divided by the modulus of rupture of 396. Okay? It's just automated. The erosion factor, we have to go and read it. So dowel joints, yes. Concrete shoulder, no. And it was suggested we go with 150. The bearing capacity is 55. So for the single axle is somewhere between 3.2 and 321. It's closer to 3.2. You see the difference doesn't, so I can calculate it, of course. But very soon you will see we don't have to refine that much. If you really want to calculate, you know, the difference between these two, and then you divide that by 4, and then you add that to 2.50, pardon, 3.2, and that is your exact value, if you wish. Now, we also have the same for tandem. So we have equivalent stress for tandem. Equivalent stress for tandem with 150 and somewhere between 40 and 60 is the right-hand side of this pair, each pair of numbers. So that is somewhere between 204 and 223. I'm interpolating. You understand what I'm dividing by 4, right? because I'm in 55. So between 40 and 60, if I divide by 2, that will give me 50. If I divide by 4, that gives me 45, 50, 55. And if I add it to this one, moving from 251 to 270 or 204 to 223, if I add that quarter to 204, will give me the 55. So it's 20875. And the erosion factor will be somewhere between 327 and 330. I can very quickly probably know that it's going to be roughly 328. Now, my groups. These, as we explained, are the highest weight of each group. So my highest, my single axle, the groups, the highest value for the first group is 133. That's the value I have here. The next one is 125. That is the next value. The next one is 115. You can see it here. 107, 97.8. 88.8. 80. The next one, if I need it, is 71.1. The next one, and so on and so forth, okay? This is the safety factor multiplied by 133. So it is simply 1.2 times 133. The 150 is 1.2 times 125. If you don't believe me, you can try it. And the same for these values. Now, this is the load, this is the weight I experience maximum in the axle. Now, I need to estimate what is the number of repetitions that I observe. So the number of repetitions is going to be based on the trucks that I have times this percentage. So 0.58 multiplied by 12,951,113 divided by 1,000. 0.58 multiplied by 12,951,113 divided by 1,000 will give me the 7512, okay? The next one is the 135. So 1.35 multiplied by 12,951. I don't need to really make the division if I just express this in thousands, which is what the approach suggests. So you have 17,483. That's why you have 17,485 there, because we are rounding it up. The next one, 35,000 is coming from 277 per thousand. So it is 2.77 by 12,951, 35,875, and so on. Okay, is this clear so far, guys?
Yes.
Okay.
Yeah.
Now, we're gonna go now into the allowable repetitions. For the allowable repetitions, oh my goodness, can you guys see this ad coming? This is the pivot that I was talking about. So it's 0.6458. So we have 0.6458. So let's see where that is. How much did I say? 0.6458. 0.64 is there. Okay, this is 0.6, this is 0.7. Now I'm gonna go with the highest weight. My highest weight is the 160. Single axle load kilonewtons is this one's over here. Tandem axle is this one's over here. So I go with the 160. And I have to cross through the pivot. I'm gonna zoom out, guys, because it's easier. The value, if you see, this is allowable repetitions here. This is 10,000, this is 1,000, this is 100. And this arrow is going below the 100 repetitions. So it's going to almost 0 repetitions. The pavement has no capability. But even if you put the 100, this is already at a 7,000%. So who choose the 150? Now nobody did, right? So what happens, guys, is that the pavement with 150 millimeters has no capacity for this amount of traffic. 12.9 million, it cannot handle it. So we have to increase the thickness. Somebody else, please, another thickness, and please increase significantly.
300.
Hmm? You say 200 or 300?
300.
300. Okay. So now notice. I'm gonna try 300. My sub-base subgrade doesn't change. It's still the same. I go with the 300 here. This is still the same approach. I will be somewhere between 0.95 and 102 for equivalent stress. So it will be 0.9675. The pivot will be 0.24, okay? The erosion factor needs to be estimated. For 300 is somewhere between 2.3 and 2.31. So I'm just gonna put 2.3. The equivalent stress for tandem is somewhere between 0.89 and 0.99. So it is 0.10 divided by 4. So it is 0.89 plus 0.10 divided by 4 is 0.025. So it's 0.915. And the erosion factor will be somewhere between 2.5 and 255. Halfway, which is 50, is 252. And halfway between 250 and 252 is 251. And a little more, but let's just say 251. So now we go and we try again. My pivot is 0.24. My pivot, oops, doesn't want to grab the pivot, is 0.24. This is 0.2, 21, 22, 23, 24. The allowable repetitions are 10 million. You have consumed only 0.08%. We go to the next group, 150. You see how I am here in 160. Maybe I should put like a circle here. So I move now to 150. The right-hand side is tandem, okay? The left-hand side is single. I need to cross through the pivot. When I cross through the pivot and I go above 10 million, this is called unlimited or infinity. That means that for single loads, I only use 0.8%. Now I go for tandem. For tandem, I go with 277. So for tandem, I go with 277. This is 280, this is 260. So I will be slightly below the 280 for the 277. Once again, for fatigue, the arrow will go beyond 10 million. This will be considered as unlimited. The total that you have used is 0.08%. I can go to the erosion so you can see what happened. I will go to the 2.3 as erosion factor. So my pivot is 2.3. There. My initial value is 160, this one over here. I'm reading somewhere between 10 and 20 million. So let's say 15 million. The next one is 150. I am reading a little more than 20, a little less than 30. So I'm reading 25 million. The next one is 138. I am reading 60 million. The next one is 128.4. And I'm reading more than 100 million. In this case, this is called unlimited. I go to my tandem, and my erosion for tandem is 251. This is 2.5, 251 will be roughly there. I go for my first value tandem, 277. This is 280. So 277 will be slightly below. This is 7 million. The next one is 255. The value will be 15 millions. The next one is 234. The value will be 28 million. The next one is 213. It's already unnecessary what I'm doing, right? But it's just so you realize that. Let's see if you get to the right conclusion. So the allowable is 70 million. And the next one is unlimited. So what is your conclusion? This is fatigue. This is erosion. And this is for 300 millimeter thickness. Conclusions, guys, so far. What shall we do? We accept the design. We go with the 300 millimeters. We reject the design. Go ahead.
Yeah. Because wouldn't Shinhan be like too expensive for the initial cost?
I couldn't get you right, but I think you are saying it will be very expensive.
Yes.
That's correct. You are wasting your money. You are creating a thickness that only is used at a 2%. So we really need to bring this thickness down. So I'm going to bring the thickness down to, let's say, 230. I am somewhere between 138 and 148. So I'm at 1.505. And in erosion, I'm somewhere between 264 and 265. So let's say 264. That's for single. And for tandem, of course, I need to erase these values. And for tandem equivalent stress, somewhere between 121 and 134. So I am in 124.25. And the erosion factor for tandem is somewhere between 278 and 282. So 280 will be halfway. Halfway will be for 50, but I have 55 almost. So it will be 279. So I go with my 160. Oh, sorry, what is the pivot? The pivot is 0.38. There. So I go with my first one, 159.5, 160. $900 is not enough. 240. $130 to $139. So it's 132.25. And the erosion factor somewhere between 258 and 260, so 258, because it's closer on that side. And for the tandem, somewhere between 115 and 128. $118.25. And the erosion factor somewhere between 273 and 278. This one is easy because you have 5. So halfway is 2.5 and halfway is 125. So 125 plus this is 274.25. And now we go back again with 0.334 as pivot. This is 0.3, 31, 32, 33. So 0.334. We go with the 160. And allowables are, this is 20,000, this is 10,000, this is probably 14,000. 53% is consumed right now. It doesn't give me much hope. I'm gonna run one more, but I think it's rather better to increase another 10 to 250. But I'm gonna run one more. So I go now to 150. And I'm reading 30,000. You see, it's gone. So I have to increase to 250. Somewhere between 122 and 132. $125.25. Erosion, 250. Somewhere between 253 and 254, but it's closer to 253. You can interpolate if you want, right? But you will see very soon that this is just a pivot point, So the decimals in excess really don't matter that much. And for tandem, $109 and $122. $112.25. And the erosion, $269 and $273. $270. Okay, so I think this one is the winner. Pivot is at 0.316. $160. $30,000. $150. $70,000. $138. $300,000. $128. Remember, I'm reading on the left because it's single. This is, let me see, 1.5 million. $117. Voila, unlimited. I still have to run the tandems. 277. Oh, and what is the pivot? The pivot for tandem, for fatigue, is a stress ratio. This is the pivot. It's 0.28. And remember, I have to read from the dowel, yes, shoulder, no. .28, I said, right? 0.28. So I go with the first one, 277. $5 million, maybe a little less, 4.5. $255. Unlimited. I have used 67% of the fatigue life. What about erosion? Fingers crossed. So I will go with 253 as my pivot for erosion. This is without concrete shoulder, as you can see here, okay? So we're using the one on the left. The one on the right is with concrete shoulder. And the pivot is 253. Two four, 2.5, this is difficult, 2.6. And I go with my first one, 160. This is 2 million, this is 3 million. So I will say this is 2.2, 2.3 million. $150. $3.8 million. $138. Six is yes above 6 million. Let's say 6 million to be on the safe side. 128. Is just above the 10 million, but let's say 10 million. $117. $20 million. $106. $40, just above 40 million. $96. It's unlimited. But this is single axle. I still have to add the tandem, and the tandem will be the surprise. So 277. And for tandem, I have to use the new pivot, 2.7. $1.9 million. $255. Cross through the pivot, and we read here. How much do we read? 3 million, maybe? Just a tiny more, maybe 3 million. $234. $5 million. $213. $10 million. 192. $20 million. You see how the percentages are increasing. 170. $70 million. $150. Unlimited. And this is 250, right? What do we do? Because we already tested the 240 and it failed, if you remember. What do we do? Guys, I'm waiting for you.
I'm sorry, what is the question? I wasn't paying attention.
The question is, what do we do about this design? We have 67% fatigue. This is the percentage of fatigue. And we have 20% erosion.
Increase the thickness of it.
Increase the thickness, it will drop the fatigue and it will drop the erosion.
So decrease the thickness then?
I can decrease it. I put it in 240 already before and it failed. This one went beyond the 100%.
Can't you go 245 instead of 240?
I could try something like that, but if you notice, the tables go by 10 cent, because this is millimeters, right? So 250 is 25 centimeters and 240 is 24 centimeters. So do you think a contractor can do 24.5 centimeters? Will it make a difference between 25 and 24.5?
No.
There are other things we can do.
Adding a shoulder, does that help?
Oh,
It would be a different graph.
Here we go. So you can make a concrete shoulder. That will help. What other element can help? A hint on screen for you. Right now we're using a 100 untreated.
So we could increase the sub-base thickness.
Increase or decrease?
Decrease.
Yes, you could decrease this or eliminate and put it directly on the soil. Because if you see, we are at 67% fatigue, so you still have another 33% room. But in erosion, you still have a 80% room. So erosion is not a problem. Fatigue is the one that is getting close. For fatigue, concrete shoulder, no concrete shoulder. That is the main element for my fatigue, as Lana clearly identified. For erosion, I have the dowels and the concrete shoulder. So the dowels play a role in the erosion. I already have dowels. So from this perspective, I could drop in terms of erosion and probably still pass, but it will fail in fatigue. So I will have then to do something in terms of fatigue to increase the resiliency, probably adding the concrete shoulder. Is the approach clear? What we do? It is always equivalent stress, erosion factor, the stress ratio is your pivot. From your pivot, you go and you read the allowable. You enter the allowable here. And you do that also for erosion, where you will go here and read from this table. What happens if you have a road that is new, doesn't exist? From where do you get this 15,000?
From models, or you take it from roads that are close to the existing, to the one you want to create?
From a macro simulation model, strategic transportation model, where you have estimated your ADT, or from similar facilities. The same as the GROW, and the design period is pretty standard. Now, another factor we have at our disposal is the type of concrete, right? We have assumed a specific F prime C for the concrete, but you can change it. So that is also there. So you have multiple factors that you can play with when you are dealing with this. Okay, in the Excel, you have all the different charts that you need, okay? So all the charts that we have been using in the lecture are here in the Excel. Notice this. This is for erosion factor. So we have dowel joints, concrete shoulder. We have this other one that is called aggregate interlock joints, concrete shoulder. What do you think is the aggregate interlock joints? Let's see if you have ideas. Should I leave it for the exam?
Are they like the pavements that interlock with one another, like in those pedestrian areas?
Yeah, maybe. I'm not quite sure what you mean by those pedestrian areas, but you see both have concrete shoulder. So concrete shoulder is the same. One has dowel joints and the other one doesn't have the joints, the dowels on the joints. It has an interlock. So it is like a tooth kind of style to lock in the slab. But that is not a load transfer mechanism. So this is no dowels. The 8B is no dowels. And the 8A is yes dowels. Now, we have 7A, 7B. Dowels, yes. Concrete shoulder, no. Dowels, no. Concrete shoulder, no. Dowels, yes. Concrete shoulder, yes. Dowels, no. Concrete shoulder, yes. So those are the 4 circumstances you have. So you have 4 tables for erosion. While for fatigue, you only have 2 tables. Concrete shoulder, yes or no. So fatigue is not affected by dowels on the pavement. Pardon, fatigue is not affected by dowels. Okay, so this is the main distinction you need to get out of this, how they are affected. Finally, before I finish this class, this is average figures for USA statistical information. And you only use this when you have no information for your road or your jurisdiction. If you have information, you don't use these values. Okay, I can do another example, but I think the method is repetitive and I already did like four or five of these by iterating between the thicknesses. Now, what will happen? Let's imagine these percentages are 101% here and 25% there. Do you accept or reject the design? This is again a question for you guys.
I would accept it. Because 1% isn't that much.
Okay, but that means you are using more than what you have. The capacity is being exceeded.
I have a question. So earlier we rejected the 67.65 because it was over 50%.
No,
So-
we didn't reject it. The 67 and 20 is accepted.
Okay, my bad.
But if one of them goes beyond the 100, you have to reject.
But if it's only from 1%, there's already like security factors in the calculations. So isn't that correct?
You are contradicting the method. The method states that when the design goes over 100% in any of the two, you have to reject it.
All right.
If this is 98% and this is 98%, or let's put it like this is 99% and this is 99%,
Yeah, that will be fine.
that will be fine, correct? If this is 67% and this is 1%, or is similar to what we have here. If one is always going to be higher than the other one. Which is which depends on what you have specified as dowel, yes or no, shoulder, yes or no, F prime C of the concrete, okay? When you have one that is much bigger than the other one, you have to identify what affects this, what affects that. This one has room for dropping the thickness. This one has very little room for dropping the thickness. So you need to target what will increase the capacity from this perspective so that you can drop the thickness, if possible. Of course, if you are already in the 87% and the 53%, you probably don't try anything, right? Even the 67% is already a bit high. You can stop there. It is fine. You are already consuming a 67% of the life of this. If you can try to do little adjustments.
And we don't have frost or swelling here, right?
You don't have what?
In this method, we don't have the frost or swelling to be taken into account like the other methods.
No, there's no frost heave and there's no swelling in this method. It's correct. Okay, guys, that is the PCA design approach.